3I Atlas has now exited the gravitational influence of Jupiter, completing a precise passage through one of the most powerful regions in the solar system before continuing outward on a trajectory that will carry it back into interstellar space. It never slowed, never settled into orbit, and never behaved like a typical solar system object. Like Oumuamua and 2I Borisov, its hyperbolic path suggests an origin beyond our Sun. But its speed, composition, and activity hint at something more complex, moving at nearly 70 kilometers per second and carrying unusual chemical signatures. 3I Atlas is not just another interstellar visitor. It is a rare fragment of a distant environment, and possibly a sign that what we have seen so far is only a small glimpse of what exists between the stars. Early analysis focused on confirming this trajectory and monitoring the object's interaction with Jupiter's gravitational boundary. Ray's astrophotography, working through observational datasets and imaging, identified the moment when 3I Atlas effectively disengaged from Jupiter's sphere of influence and resumed a more predictable outbound path. That confirmation established a baseline. Whatever 3I Atlas is, it is not a typical resident of the solar system. From that point onward, attention shifted from orbital mechanics to physical properties, what the object is made of, how it behaves, and whether it conforms to known models of cometary activity. The trajectory itself remains one of the defining characteristics. Unlike objects that form within the solar system and settle into elliptical orbits, interstellar visitors follow open-ended paths. 3I Atlas appears to have entered from the outer regions, with its incoming direction suggesting an origin far beyond the orbit of Neptune. Its motion through the solar system has been described as smooth and continuous, shaped by the sun's gravity but not captured by it. The measured velocity, estimated at around 70 kilometers per second, places it on the higher end of expected speeds for interstellar bodies. While such velocities are not impossible, they reinforce the idea that the object has traveled vast distances, potentially influenced by gravitational interactions in other star systems before arriving here. Attention quickly turned to its chemical composition, particularly the reported presence of methanol within its coma. Methanol, a simple organic molecule often described as a type of alcohol, is not unusual in space. It has been detected in comets, interstellar clouds, and regions where stars are forming. What drew interest in this case was the proportion. Observations suggested that methanol could account for a significantly larger fraction of the volatile materials surrounding 3I Atlas than is typically seen in comets originating within our solar system. In most cases, methanol appears in relatively small percentages, often overshadowed by water vapor and other common compounds. Here, the signal appeared stronger, indicating a composition that may have formed under different conditions, colder, perhaps more chemically distinct environments where such molecules could accumulate and persist. That chemical signature has implications for origin. If the composition is indeed skewed toward methanol and other volatile compounds, it may point to formation in regions far colder than the inner solar system, possibly in the outer reaches of another star system, or even in interstellar space itself. These environments, shielded from intense radiation and heat, allow fragile molecules to remain intact over long periods. In that sense, 3I Atlas could be understood not as anomalous in a fundamental way, but as a fragment of a different cosmic environment, one shaped by conditions that differ from those that dominated the formation of Earth and its neighboring planets. At the same time, the object's physical behavior has drawn equal attention. Observations indicate that 3I Atlas is actively releasing material, producing a coma and ejecting dust into space. What stands out is the nature of that dust. Reports describe grains significantly larger than those typically associated with cometary activity, reaching sizes on the order of hundreds of microns. These particles are not merely drifting away. They are being expelled at substantial velocities, measured in miles per second. Such behavior suggests a strong and sustained outgassing process, in which volatile materials within the object are heated and vaporized, carrying solid particles outward with them. The rate of this activity is also notable. Estimates suggest that 3I Atlas may be releasing material at rates approaching 1,000 kilograms per second. For comparison, this places it within the range of highly active comets, though the composition and structure of its emissions appear somewhat different. Rather than producing a fine, diffuse tail dominated by small particles, it seems to be generating streams of larger debris, giving its surrounding cloud a denser and more structured appearance. This pattern aligns with observations of evolving coma shapes and tail configurations, which have changed over time as the object moved through different regions of the solar system. Data from space-based observations has added further context, though not all of it has been publicly detailed. The JUICE mission, operating in the vicinity of Jupiter, captured imagery of the object during its passage through the region. While only limited visuals have been released, they show a bright, active body with a clearly defined coma. Additional observations attributed to Tianwen-1 suggest that changes in the coma and tail were detected over multiple days, indicating a dynamic system responding to external forces such as solar radiation. Those observations also reinforce the idea that solar radiation plays a key role in driving activity. As 3I Atlas moves through space, sunlight heats its surface, causing volatile compounds to sublimate and escape. This process generates jets, localized streams of gas and dust that can extend outward in specific directions. In many comets, these jets vary in orientation and intensity depending on rotation and solar exposure. In this case, however, reports suggest that some jets have maintained relatively consistent angles over time. While not unprecedented, this stability raises questions about the internal structure and rotation of the object, as well as the distribution of volatile materials beneath its surface. Another aspect that has drawn attention is the object's brightness profile. Comets typically become more active and brighter as they approach the Sun, where increased heat drives stronger outgassing. As they move away, activity usually declines. For 3I Atlas, however, there are indications that brightness did not follow this expected pattern in a straightforward way. At certain points, the object appeared to maintain or even increase its brightness, despite increasing distance from the Sun. Such behavior can occur under specific conditions, such as when new regions of volatile material are exposed, or when structural changes reveal fresh surfaces. Nonetheless, it contributes to the perception that the object is not behaving entirely in line with standard expectations. The passage near Jupiter adds another layer of complexity. Jupiter's gravitational field extends far into space, creating a region where its influence can alter the paths of passing objects. 3I Atlas approached this region closely, but did not experience a dramatic deflection or capture. Instead, it passed through with its overall trajectory largely intact. From a purely mechanical standpoint, this is not unusual. Many objects traverse planetary gravitational fields without significant changes to their paths. However, the alignment required for such a passage, approaching, skimming the boundary, and continuing onward, can appear precise when viewed in retrospect. It is a reminder that orbital dynamics, while governed by deterministic laws, can produce outcomes that seem finely tuned. There have also been discussions of non-gravitational forces acting on the object. In cometary physics, outgassing itself can generate small but measurable accelerations, subtly altering an object's trajectory. This effect was notably observed in Oumuamua, where deviations from purely gravitational motion were attributed to the release of gas. For 3I Atlas, similar mechanisms may be at play, though confirming them requires precise measurements over time. If present, such effects would further complicate efforts to model the object's path and reconstruct its origin. Size estimates introduce yet another variable. Some interpretations suggest that 3I Atlas is significantly larger than previously observed interstellar objects, potentially by orders of magnitude. If accurate, this would challenge assumptions about the typical scale of such visitors. Interstellar space is vast and largely empty, and smaller objects are statistically more likely to travel long distances without being disrupted. A larger body surviving such a journey, while not impossible, would prompt questions about how it formed and how it maintained its integrity over time. The possibility of Earth intersecting with debris from 3I Atlas has also been raised, particularly in relation to seasonal increases in observed fireballs. Each year, Earth passes through streams of debris left behind by comets, producing meteor showers. The suggestion here is that some portion of 3I Atlas's emitted material could intersect Earth's orbit, contributing to observed fireball activity. While this remains speculative, it highlights the broader connection between cometary behavior and phenomena observed in Earth's atmosphere. Even small particles traveling at high velocities can produce visible effects when they enter the atmosphere and burn up. As these observations accumulate, interpretations diverge. On one hand, 3I Atlas can be understood as a natural interstellar comet, an object formed in a distant system, shaped by extreme cold, and now revealing its composition and structure as it passes through a warmer environment. On the other hand, the combination of high methanol content, large dust grains, sustained activity, and unusual brightness patterns has led some to question whether existing models fully capture what is being observed. At present, there is no requirement to invoke unknown physics or artificial explanations. Each individual feature can be accounted for within the framework of known processes. What makes the object notable is not that it defies explanation, but that it brings multiple uncommon characteristics together in a single case. As 3i Atlas continues its journey outward, opportunities for direct observation will diminish. The object will grow fainter, its activity will decrease, and eventually it will become indistinguishable from the background of space. What will remain are the data collected during its brief passage, measurements of its motion, spectra revealing its composition, and images capturing its evolving shape. These records will be analyzed over time, compared with other interstellar objects, and used to refine models of how such bodies form and behave.